Hello, everybody. Today we will continue our Zoom meetings, and today the subject of the meeting is spectral analysis and dynamic system identification. But today the meeting will be something different, special. If you remember the last meeting, we discussed the manner of considering the subjects, or that you get an empty Matlab scripts and we will work together and you will continue to fill all lines and run the commands. Or another way that you will get everything already written in Matlab script and just follow me, maybe with explanation, and run each section differently. And Adeli, one of our participants, it already built a nice questionnaire that we will send today after today's meeting, and we will ask some. There are very little questions about which manner of consideration you prefer, or work together line by line, or get everything in a ready manner and just listen to explanation of the subject. And we ask you to fill this Google form, and Adeli at the end will send us to Reuven Katz, Professor Katz, and then in the future it will be much clearer what will be preferable for future our meetings, not our, but future meetings at all. Okay, do you have some questions about starting about this Google questionnaire? Okay, let's start. I open share screen. And again, you already received Matlab script. It's not just regular Matlab script, it's a live editor script. It means that it is written in a special way, and to run each command or each section in this script, live editor script, you can press button run section. Here you can see on the ruler upper start, you can press run section, or you can press two buttons, Control and Enter, and run the section where the mouse already is located. Okay, before we'll start with the analysis of signals and the spectral analysis, we should have these signals, and Matlab has a lot of way to build signal as data. And most toolboxes in Matlab, they require to begin with the data in vector representation in time base. And for building this data, Matlab and toolboxes, they prefer vectors in vertical manner. It means that it should be, if it times, built in column way. Let's do it. For example, first, for each data built in a digital way, we need sample frequency, for example, 1000 Hertz, and we will start from the time. The time will start from 0 to 1000, and the increment will be also 1000, and totally we'll get 1000 point, and we can just run this section to see that really size of our time is 1000. Now, when we have time, we can continue our estimation of our data. Let's take as an example of our data is sum of two harmonics, two sine wave. The first harmonic it has larger amplitude 4 and the frequency 20 Hertz, and the second harmonic is a smaller amplitude 1, and the frequency is a little bit higher, 35 Hertz. And we can plot this sum of two harmonics against the time, and build the labels for time and the, okay, let's run the first section of the example. Here we see that in the size of the data, really it is 1001 points, samples, and it is a vector, vertical vector, and here is just, we can see the data as a graph, signal against the time. Matlab has, and not only Matlab, but toolbox, signal processing toolbox, it has a number of tools to produce signals. For example, it has chirp command. Chirp, it uses 4 input parameters. Here, this is example of another signal built as a chirp. The first is our time, is a vector. The second is the frequency at the beginning of the time, of the 0 time. The third parameter is the end frequency at the end of time, and this is the 0. It's a 0 frequency at 0 time, and t, and third is the maximum t, and the last value is the maximum frequency at time, the third time, number 1. And let's see how it works, this chirp. Again, we can see we have the same time, but we start from 0 frequencies practically as a constant value, and we finish with the frequency 50 Hertz. At time of 1 second, we have 50 Hertz. Okay, do you have questions about chirp? Let's continue. Also, we can play not only with the vector just as a chirp and sine wave. Also, we can produce Gauss Pulse, for example. Gauss Pulse also, it has 3 parameters. For Gauss, we have the time. The first parameter is our time. The second parameter is a carrying frequency, the middle frequency, the carrying frequency. And the last one is the bandwidth of the Gauss pulse. And again, we can see the size of our pulse and plot it as a graph in Matlab. Let's do it. I just can press this section and see the pulse, the Gauss pulse. Here the example. The only difference from harmonic waves, the Gauss pulse, from the left side, it produces 2 variables. From the left side, you can see 2 variables. It means that it can produce the real part and the imaginary part of the Gauss. And we can plot both of them as a graph, as a function of time. Again, we already know that we can produce a random signal, and random signal also require the length of this number and the size of the vector. For example, if we need only 1 column, it should be a number and only 1. Let's plot this random signal. We will run here the example. In the chat of our previous meeting, I read that you already know that we can fix the seed of these random numbers in generation to get the same each time. For example, if I will run this section of the script, you can see on the graph that each time we will get another random data. You can see each time it is something different. But if we need to stop it just to fix, we can ask this random number generator and choose any seed, any positive number, for example 1. And now when we run this script, we will get each time, we will get the same random data. Okay.
Can I ask a question?
Yeah.
In line 9, the vectors yi and yq, how Matlab knows that it should plot also the time? I didn't like.
Here we can plot the time. I didn't use. First, we will shoot. Why I put here the line number 8, just to show you that for number 8. You can see it's a vector, but it's not a column, it's a line. It has 201 numbers, but in a line. And if I need to plot they all together, I need just to make a transpose. This is why in number line there is a sign of transpose. You can see it, right?
Ah, okay. No, I thought that. Okay, then what we see here is. The amplitude vs the phase.
So let me show you. Here you can see this time. I can put it inside. Let's do it. If I put this time vector here, we will see it the same Gauss pulse, but now against the time x-axis. Can you see it?
Previously, what was the x-axis?
The time now here is the vector of time.
Yes, I understand that now we can see the time, but before that, what the x-axis was?
Before time, if I don't need time, for example, we just can see number samples, number of the samples. Okay, let's start it again without time. Here the number we ask 201, and here you can see these 201 numbers. It's just numbers.
Okay.
What is 0.5?
It's a bandwidth. It's a bandwidth. I can show you when we try to make it smaller bandwidth. You can see the difference. You see, this is the bandwidth of a Gauss filter. When we get this larger number, we get this kind of image. It's bandwidth of the Gauss pulse. It's width.
Okay, thank you.
Okay, we stop about the random number generator at fixed seed. Also, we can have, for example, those who need a sawtooth signal. We can use it just the same as sine. You can see here this our time, and the second number, second parameter. Let me explain you. When I run this section, you see we get the pure triangle or sawtooth signal. But if we choose it from 0, for example, we get another kind of triangle that from the vertical line goes down to the right side. When we use here 1, we get another example of these sawtooths. And you can use any of them that you need. But when we choose this half of 1, we will get pure triangle. Okay. I think it's clear. Also, we can build a sync function. Do you remember that syncs is just sign of argument divided by the same argument? We can see this example here. Also, if you need, you can produce this signal to make an analysis. Generally, we play with all these signals. We need them as input to our system because the standard signal, which we are discussing now, they are good standard to test something. When you put sine or random signal, you can just understand the output of the system and get everything and know everything about the system. Also, here is example, again, this example of square, next example of square, just again, it's absolutely the same as sine wave. Let's try. Here you can see the square example. Also, we can play here with the frequency. For example, I choose 40. When we take this smaller number, we will get less number of periods. Here, the twice less. We can make twice more. Okay. Also,
Michal,
yeah.
can I have a question? In line 16, why we start with and in the argument?
Okay, because function sync, it only works for the half of the, from 0 to positive number, positive time x. But I would like to show you all the function from the negative to positive. We start here, we have two branches of time. Let me explain. Here, I will divide them. The first one, it's our time. We already get this t, we know our t. But the first part, you can see we took the time from the end with the increment -1, and we finished with 1. It means that we just inverted our time. We go back. We started from the end and finished with the beginning of the time. Then we connect to this negative time. We connect our positive time, and this way we'll get all this time. Let's plot again this, what we did before. Now we will do now. I took from here the time vector, and I plot to the sync function, and I ask seek to plot. Here we plot this sync function just samples, but now we will plot it as function of time. You see, our function starts from the -5 till 0, then we continue regular part of time, just a regular way.
This is
Great,
just to
thank
get
you.
the symmetry, like to get symmetric image.
Yeah, sync. Yeah, it's sync. Generally, if our argument sinus x, if we start x from negative parts, from negative values, yeah, it's a symmetric function.
It's just that you are using time, so negative time. Why do we need something like this?
Because functions let me again.
No, the function I know it works asymmetrically, but
no, I have no negative here. I have only positive t. But to show you all this range of the argument, I need something negative. I can't just put something arbitrary, or if I have something, I just invert it to the negative part. It's up to me.
Okay.
It's just arbitrary. You just use any kind of negative number to plot this sync function. Okay, square we discussed. Now the voltage control oscillator. It's a more complicated way of generated signals. Here in this voltage, we can plot the signal according to the argument in the voltage. Voltage control oscillator, it works this way. It takes from the first parameters, it takes the frequency of the signal. It has always amplitude ±1 volt, but its frequency depends of the x, our first argument here. The second parameter, which now is 40, is just the carrying frequency, the frequency, constant frequency. And the last parameter, f, it's sampling frequency. For example, let me show you, for example, the first example. We will close the second one, and we plot the result of y. You see, amplitude of our signal, it's always constant. It's just from -1 to +1. It's the same. But the frequency of the signal, it goes according to our numbers. You see, I started from -1 to 1, and then again from +1 to -1. This is why the frequency it goes from 0 of the signal, then maximum when 1, and then again to 0. To understand it, maybe we can just plot another example of this voltage oscillator when we have zeros. The first 100 numbers, it's just 0. The next is our carrying frequency and the sampling frequency. Let's see the result. Now we'll get just the constant part of sine wave. Okay, is it clear? We can, here you can take this number maybe to see another frequency. Now it's just the sine, pure sine wave. Have you some questions about this voltage controlled oscillator? It's very power instrument when we work with the experiment in a real experiment, because Matlab, you know already that Matlab can be connected to the real data acquisitor system, data analyzer system. And again, to produce something varying in time, it's very, very convenient to have this voltage control oscillator to play with the different frequencies of our input.
Okay. Can you please explain again the first vector that you put inside
the first vector is the first vector, or it is the required frequency or changing frequency of this generator. This is what I need. If zeros, it will be this constant frequency, which is equal to the carrying frequency here. But if here the first parameter is varying, as we had in the first example, it will be changing from according to the number. Now we have only zeros, only zeros. This is why we don't need to change something with just pure carrying. We have here pure carrying wave, 30 Hertz.
I don't understand what is the meaning of negative frequency.
Meaning of what?
Negative frequency. You put -1 in the.
No, it's not. It's not. Let me. Okay, if I understand what your question. Let's put ones. Also, we will get, for example, 31 and. Once. No, how to read once this way. Let me check. Or maybe I just put it here. Okay. What we did, we just use this voltage generator as the first parameter is just 4 numbers -1. It's not the negative frequency, it's just we ask the generator produce zero frequency, just DC signal without any changing in his frequency. Minus as a first parameter means the 0 initial frequency. Minus any minus numbers in the beginning means 0 frequency. It's not negative frequency, it's 0 frequency. When we ask minus, we will get DC signal. Can you now understand, or till it's something not clear?
So it is like it is shifted by 1. This is the.
Oh. No, the generator it takes from this input parameter, the first parameter, it takes how to play with the frequency, how to change it. If there is a minus, it puts 0. If there is 0, it puts the number of the carrying frequency. If there is 1, it takes the maximum frequency that we ask for carrying.
Okay. Okay.
You know what? If my sorry, maybe my English, but you can do this way. You can press right button in live script and go to the help. And in help, even you can open the help in a browser. And here it explains everything, creates a signal that oscillates at a frequency determined in the real input vector of array X. The first is just our controller of the frequency. Just maybe this example will be much maybe clearer with my English. Okay, now the yeah.
Can I ask something about the phase? I don't see anything in the help section. What if I want to create a phase between the signals? Let's say creating a signal of a sine and a signal of a sine with different frequency, and I want to have a phase between them.
We will discuss the phase result when we go to the frequency response function. But here we can just put it. Let me show when, for example, here we can put 2 radians in the next harmonic, and when we start it, we will get the result shifted. The next one, the higher frequency, will be shifted in phase by 2 radians.
But in the VCO, I cannot do that.
No, no, because it's just the signal, only one channel's output. Here you will get only one channel, and phase, it means that you need something at least 2. Phase, it's a relative characteristic, something against something, okay? But if you have only one, it's difficult to speak about phase.
Okay, thank you.
Okay, we have in Simulink, if you, for example, if you mean using Simulink, Simulink also has a special generator, and there are special settings for phase. For any kind of channels, you can produce 10 channels, each one with its own phase shift. Okay, the next example is producing the impulses. The impulses, again, we'll have the time as a vector. Again, it's a column vector with the transpose sign. And when we choose the impulse is equal to t equal to 0, it's just the number, only number that it can exist in the time equal to 0. The next one, it's unit step. It means that it will be it will be when t is more than 0, and the ramp is just t multiplied by our unit step. If our time is just linear increasing function, this means that our ramp also will be the time varying, time linear increasing function. It will also, here we'll have an example of quadratic changing impulse. And let's plot everything, all these 3 examples all together. We will plot against t. We will plot our impulse, short impulse, and then we'll hold it and we will plot each one together. Let's do it. There is an example of three impulses. We will have here the impulse only it exists when we have 0. Also, we have the unit step only it is 1 when we have time more than 0. Ramp, which is increasing linear, increasing in time, and quadratic changing impulse also as a function of time. By the way, let me ask you, do you see my mouse in here in the plot?
Yes.
Okay, because I don't know if sharing also produces the mouse moving. Okay, also very important function. Let me ask about the questions because maybe we are going too fast. Okay. We'll continue. Now, very important Matlab function, repeat mathematical sentence. What it means, if we have something as a function, for example, y, we can repeat the same function 3 times, for example, and as a vector, it will be the second number, the second parameter, just ask to repeat 3 times, but only as one vector. Let me show you, for example, when we have, maybe first we will plot the y. Plot y. And we just comment our repeated results. Here our function y. You can see it. It was from the very beginning the sum of 2 sine waves. But when we repeat 3 times this function and plot the result of this repeating, we will get something else. Here we can see that we repeat 3 times the same signal, and I asked to show you the result of the size of the before repeating and after repeating. And here you can see that the small vector was 1000, and now we have 3000 samples in the same repeated vector. Also, we can use a signal generator that it is built in Matlab. Let's do it. I will close everything and open this signal editor. Is a special graphic user interface built specially in Toolbox and Signal. And we use it mostly only in Simulink. Let me show you. We will start this signal editor. And it is a large window. Let's make it smaller. Okay. Here we can build our signal just manually as a graph, as a picture. We will start from, it is already help us, please, to start, use insert. Here we'll insert, we will draw our signal. For example, we will start from points. And for example, each time I press button in the screen, we will get something as a function. Also, we can just put here, not points, we can put here lines. For example, I can put this line. It will be this kind of signal. We also can put here examples of expression. Let us put here something, for example, 6 and increment this one for 8. And let's build this as a sine wave. And we will get our function. Okay, and apply. Here you see a part of sine wave. Also, this graphic user interface allow you to remove some points, which is not, or maybe move some points. For example, if not, I don't like my points here, I just can move it here. I also can erase, maybe erase this point. And we can use this example to build our signal itself as a graphic. And yeah.
How you got into draw?
To what?
From insert, how you got into this,
okay, let's do it again. Okay, I just close everything. We don't remember it, okay. Here, this screen, you have it, right?
Yes.
Okay, this section in the middle, it calls insert. You can see here insert. I start button signal, and I choose. I could, if I have some, but I have no author signal. I started from nothing. I started from drawing signal. You can see this menu, okay? and I choose this drawing signal. Now I have another screen and here we can have point, line, expression, and drawing. Can you see it?
Yes.
Okay, I started, for example, with point. Oh, now it doesn't work, this graphic interface. Maybe it's not good to close. Ah, no, it's okay. I can do this way my signal. Okay, here you already have the signal. Also, you can just make a screenshot, just make a graphic photo of your signal. You can insert your signal in the workspace of Matlab. For example, you can choose this name of this signal. Let's take it something shortly, for example, S1, and I can insert it in the Matlab. Okay, now you can see the scenario and signal is S1. And again, when we go to our Matlab workspace, and here I ask about something that started with S. No, no, because we are not in our, where we are here, we should be in our lessons. I believe it's here. You see here the example that I already built S1. We can plot this signal in workspace and in graphic and regular graphic signal. How to do it? Let's do it. Okay, I close this example of signal editor. No. And we will return to our live editor. And here we can load our S1 mat. Let's do it. No, sorry, I opened, sorry, I don't need it as a signal generator. We will close it. It was my fault. We don't need here a signal generator. Okay, let's just the signal. You can see the signal now is a structure. To see the structure, we just need to see the values of this. The value is this way. Time is a signal dot values time, and y is a signal dot values data. Let's see if it works. Okay. Do you remember I plot the signal by hand? I think that it's a very beautiful sine wave. Okay, some questions, please, about the signal editor.
Can you show, please, how to enter to the signal generator again?
You know, it's not so popular. It's just for those people who use Simulink and Spectral way. Speaking the truth, I do not know anybody who use it, but okay, let's do it again. We close and we'll open signal generator, and we start again this signal generator. Okay.
How you go to this?
Okay, it explains. Please start using insert section from the left. You can read it, right? Insert section, this is our insert section. If we have already something scenario, you can take some scenario, but I have no, because I don't need it. I do not use it. I didn't use it but if you need, you can just start from the signal itself. Press here the button signal. You can start from the blank signal or author. Also, I don't have author signal. I started from drawing because I have nothing to start. I start from the drawing. Okay, press please draw. Can you follow me?
There is no such option in my Matlab.
But you have this window, this signal editor window?
Yes, I have it, and I have the first two choices, but the draw choice I don't have.
I don't know what to say. It's just a regular, but you see this signal. Let's close again. You hear you,
yes,
and you have all these buttons you can have.
yes.
I don't have a signal editor, or maybe I missed something, but never
Yeah,
mind.
signal editor. You should have two toolboxes: Simulink and Simulink. Do you have Simulink in your Matlab?
Yeah.
It should be, and also signal processing toolbox. If there are two of them, it should work.
I have
Maybe
Simulink,
the
but I
version of
don't have
Matlab
this.
is old. I also don't have it. I have 18B.
Maybe. And which version of Matlab do you have?
2020A.
Yeah, it's the same Matlab. I don't know what to say because, but please, guys, it's not so important how to say tool in Matlab because it's very, very random. We can use it randomly. I don't believe that you need it. Please just know that there is some tool, but maybe we will find why you have no, but till now
Okay, never mind. Let's continue. Thank you.
Okay. Okay, this we will finish the first example and we will continue with the second one. The second one also, it's all we are discussing now, it's not the spectral, just we are need to be prepared to make the spectral analysis and to prepare the Fourier transform. This is why let's do it a little bit quickly. Windowing, we should know that Matlab requires some procedure that we call windowing. What it means that in a mathematical way, we produce analysis of Fourier, for example, for the function that we take in digital computer. It is not an unlimited function. It starts from some point of time and it finished. This is why there is some errors. We know that in mathematical field, they call Gibbs Effect. It means that we started not from zero. And Matlab has a special instrument windowing to decrease the value of the signal at the beginning, at the end. This way we can decrease the errors of our spectral analysis. Also, it's very convenient way to use this filter for this window for filtering. You can see here I put the hyperbolic link to this different function of window. If you put here, we have no time to see, but you can press and to see different kind of window. Here as example, I will show you 3 window example: Hamming, Gauss window, and Chebyshev window. Each one requires the number of samples in this window. It's n. For our example, it will be 65. And some windows, in addition to this number of samples, they require the parameter as a width or different parameters. Let's start and plot all 3 windows together. You see, this is the 65 samples of our windows. It's the length of the window, and this is the different window. They just decrease. You can see that at the beginning signal, the end of our signal, we just can put the signal practically to 0. And Chebyshev window just put it exactly to 0. And this decrease our errors for the spectral analysis. We can plot this different window using the command in Mando window visualization tool. We already have 3 windows, and we can plot them together using this window visualization tool. Let's start this section. This window has 2 parts. The left part shows the time domain, our window, and also the spectral, but spectral, let's discuss it later. This is our window. And we can see the difference between, there are a lot of windows, maybe more than 50 different windows. Each one is more convenient for different kinds of analysis. Okay. Also, MATLAB has a window designer. If you don't know, if you know nothing about this window, you can just run this window designer and get the tool that will allow you to choose what you need. Let's do it. I run this section. Here our designer. What is very, very nice in this designer that here from the right side, you can choose the type of your window. You can see, for example, now we open it with the Hamming, but let's show you what I use always is a Tukey apply. Here's our example of this Tukey window. You can see that in the middle of our signal in time, we do not change something in signal, just this transfer function, it goes as it is the signal. But at the beginning in time domain, at the end, we just decreases the value of the signal. This way, we will get a very small, practically zero errors in our further spectral analysis. Have you question about this windowing? It's only, now we spoke only about the window itself, but the main task is just apply this window to our signal. Let me show how we can apply it. When we have a window, for example, Tukey window, and we have a sine wave, to apply our window, we just multiply our signal y multiplied by this window. The only requirement that they both vectors should have the same number of samples, the same size. Let me show the both together. Our 15 line just shows together the before windowing and after windowing. Okay, let's clear.
The window is something like filtering?
No, it's not a filter, because filter works in a frequency domain. We are speaking only in time, only vector itself, samples multiplied by samples. It's just regular multiplication of two vectors. Let me show you, maybe it will be clear here from this graph. I run this example. Can you see now the blue color? It's the signal before the, oh no, it's not Hamming, it's not legend, it's original. A region signal and red color and after window. After window. Let's press again. Now legend, they are okay. The blue color, it's our original sine wave. You can see it here. And red color, it's the same signal, but having 0 at the beginning and have increasing till 0 numbers till the end. Now, you feel what it means windowing. It's only in time domain, just decreasing the starting point and the ending point, just to move throughout the Gibbs effect.
I don't understand how can this multiplication reduce the errors that we have.
Because filter it has a special structure. It's not, okay, let me show you what filter is. Here I will close everything with the commands, and I will close this also with the commands, and I will plot the filter, the pure filter, what it is. Sorry, the pure window. Let's plot it. Window itself is an impulse characteristic. Let me show you. Grid on. Okay, this is our impulse. It just shows the kind of this window. Also, window, no, let me maybe this way. You see, it's a vector. And this vector we can plot this way as a vector, and multiplying one by our original signal, we will get original signal. But multiplying 0 to original at this sample, we will get 0. Maybe it's clear, not clear, more clear now.
It's like reducing the edge effect, something like this.
Exactly. It's just a window, just to throw out the end and the just decrease the value of real signal at the beginning and at the end, just it's very convenient for our next step of filtering and next step of Fourier.
Okay, thanks.
Okay.
And Michal,
Yeah.
at line 13, what is this sign, at sign?
It's an anonymous function, because I use this Tukey window, but I just asked to Matlab to read it from Matlab itself as anonymous function. We already used this anonymous function at our lectures in May, just to run the anonymous function from Matlab and use the parameter for this anonymous function. You can just ask Matlab help with the anonymous function.
Thank you.
Any function, you can build yourself your own function and just use it. Okay, now filtering. This is something different. It's not window, because filtering, they work in the frequency domain. Again, already I believe that you know that there is a low pass filter that can pass low frequency. I mean that frequencies from the left part of the frequency axis. There are high pass frequency that can pass and stop low frequency and pass only high frequency. That could be band pass filter that can pass in the middle something. They can be band stop. And also it could not only one band filter, there could be many bands. Just to show the examples, we just use only one band, but you can use many bands as you can in your own examples. Again, this filter, there are also some two different ways of building filter. There is a FIR filters, and there is IIR filters. FIR filters is how they explain, it's a frequency response infinitive duration.
Impulse.
Yeah, infinitive duration. No, IIR is infinitive duration, and FRR, it's finite duration impulse response. They each one have advantages and disadvantages. If we have time, I can explain. For example, I myself always use only FIR filter. They are long, maybe much longer, much more complicated, but they have a pure linear phase characteristic, and I can use them for analysis, for my further analysis, much better than IIR filters. Let's see examples of the filters. Here we can use the command that Matlab uses without any toolboxes. I believe that FIR1 is a standard command in Matlab that exists maybe 20 years. It only needs the first number, it's the length of the filter and the width of this filter. Here, this width of the filter is a relative value. We need a absolute value in hertz, the cutting frequency of the filter in hertz, just divide to the sampling frequency. Let's produce this filter, which here we have without Kaiser, just Hamming is default function, and Kaiser is another filtering. and producing these two filters, we can see the result. The result of our filter, we need the frequency response characteristic. Also, we have here two ways of doing it. Let's do the first way. First, let's produce these two filters. And then we will see the frequency response. There is also the function in Matlab, frequency response from the impulse characteristic B1. Let's see it. Here are characteristic of the filter. The subplot, the first subplot, it shows the magnitude. It's just the value of playing with the amplitude of the filter, and the subplot down subplot show the phase shift, how the shape of the filter is changing in according to the frequency. Also, we can use the filter visualization tools. Let's close this frequency response function and let's see our result in visualization. Here maybe it's much convenient for you. And here you can see, for example, let me show you. I ask to build filters starting from the frequency 1000 hertz. But our filter builds these results with the normalization way. It's just from 0 to 1. To know exactly the frequency, we can just make a calculation. Our 100 divide for the sampling frequency, it should be 0.03. Let's see if really we have here this number. I can ask here for zooming. Yeah, you see, this is the number that I ask to stop the high frequency, to stop them. And low frequency, we can here to pass, and we will stop everything higher than this value of the frequency. This visualization tool is very convenient because here you can see the amplitude characteristic of the filter. You can see the phase characteristic. Pressing this button, you can see the phase. Here you can see the group delay of the filter. It's also very important. I will explain it lately. And we can just see the zooming, make this zoom of the, we can just return the back of our results. We can plot grid, not gridding, and legend, and everything is allowed in this filter visualization. What we have now, we have examples of filters, and we just run this way of looking at the result of this filter. We can use a simple frequency function to make the frequency plot from the impulse characteristic of the filter, or we can use the filter visualization tool to see our results of our filter. Any questions, please?
What about the function Kaiser? What the Kaiser function is doing?
Yeah, it's also, Kaiser here, it's not the filter, it's just example of windowing. Here we can find it, if we find here this window designer, we can find this, let me show you this Kaiser. Kaiser. This is kind of the Kaiser window. This is the view of this Kaiser. It just, we produce the filter by using a special window. There, again, there are two different instruments. Window is just playing with the signal in time domain, and filtering just to playing in frequency domain. When we build a filter, here the example, here we built our filter, but before we built it, we use a window just to decrease the filter at the beginning, at the end of the impulse characteristic of the filter.
How do you decide which window is the best for your case? For example?
Do you remember at the beginning, at the first our Zoom meeting, we already considered that today signal procedure, modern signal procedure, it's half of art and half of mathematical procedure.
Okay.
There is no one way to recommend something. Just playing, just trying, and which is more convenient for your task, for your problem. Different window. I, for example, prefer Tuki just to have in the middle, not to change something in the middle of my signal, only to decrease at the beginning and the end. But you can choose any old window. There is no some recipe, universal recipe, just up to you.
Okay.
Okay, we have no time for another. Also, there is a way to build a filter with using McLennan filter, but you already have this example. You just can uncomment this and write and run this example to see the result. Also, there is a nice key to design filter. To design filter, we will use a command. It could be used to design filter, or maybe let me show you exactly. Just go to the filter design because it's maybe more clear. Let's start this example with the line 45, filter designer. Let's run it. Again, we will get the graphic user interface, and here we can choose any kind of filter as we need. For example, let's start from the low pass filter. We need to build something low pass filter. We choose here the low pass. We can specify the order. The order, it means the number of samples in this filter. Or if you don't know, you can ask Matlab to choose minimal order for according to your frequency parameters. You can use here absolute value of your parameters hertz, or you can use it relative value normalized, meaning that the one is the Nyquist frequency. I believe that you know what it Nyquist, it's half of the sampling frequency. The name of the half, it calls Nyquist frequency. The physical meaning, it means that to understand about something about the signal, we need at least 2 samples for period. This way we can just estimate the frequency or another characteristic of the signal, no less than 2 samples per period. Now, when in normalized, we can tell that we need to stop filter. Let's do something realistic. For example, let's make 100 points, and we will make in hertz. We will take the frequency. It will be standard frequency for sound, and we will pass everything before 1 kilohertz will go, and everything after 2 kilohertz will stop. Now, the weight, magnitude specification. Here you can ask what is important for us. If we need something more precise in our pass width of the filter, here we can increase this number, for example, 10. This way we can make the passing amplitude very, very precise. When we put a larger number in the stop, we will get the stopping bandwidth of the filter more precise. Let's design our filter. You can see in our filter we have passing wave of our magnitude. We can also replace here, I believe, magnitude without the decibel, just as numbers. We having 1, we just allow to signal pass this bandwidth till the 1 kilohertz, and starting from 2 kilohertz, we will stop everything. Now we can see that passing signal here having 10, here we have the very precise characteristic of the magnitude. When I replace this number and also design the filter, you can see here now and the stopping band, we have very nice characteristic, amplitude is 0, but in the passing, it's not so precise. Okay, do you have, please, question about design filter using this filter design graphic user interface?
You said that we can combine different types of filtering. So can we do it from here or just from the?
You can do it from here. Just several, for example, you see already. It also show you two. You can build it more. These examples. And you have here two bands, the first and the second. Also, you can make more complicated filters here. It's a good tool to play with the filter, especially from the very beginning. And the most important thing that here you can, I don't, let me remember, because I need this result of our filter to show you how it works. Okay, our filter, this low pass filter, let's save the result. How can we save the result? We just press the file and we ask to export our filter to the workspace of Matlab. We press export and we choose the name of our variable. Let it be numerator, num, and just export to Matlab. Now Matlab has this variable. Okay, we were speaking only about design a filter, but the most important also is just to apply this filter, how to make this filtering itself. To apply filter, we have two commands, filter and field. What is the difference? Let me show you and you will immediately understand it. First, let's make our signal as sum of two sine waves. The first sine has a frequency 600 Hertz and the high frequency addition have 5,000 Hertz. Now let's apply filter first using the command filter and plot the signal before filtering and plot the signal after filtering. Let's do it. First, let's produce the signal itself. And this is our signal before filtering. And now we will see our signal after filtering. You can see that using this low pass filter, we just throw out this high frequency harmonic and we will get our signal back. But can you see this not exactly the same signal as it was? Anybody can say me what is the difference? Applying this. Sorry, please. Again.
Time lag.
Right. After applying the filter, you're absolutely right. We will get the lag, the shifting in time. Our filtering signal, it is shifted according to the initial signal. If we work only for one signal, it's not so important. But already we spoke about phase shift. When we have several signals, we need to know the phase shift. We just need to some instrument to work without any shifting. Matlab has two ways to do it. The first way is just using the same filtering, but using command field. Let's do it here and plot the result of using this filtering. No, it's our example here. It's our example using field and plot again signal before filtering and after filtering. what is field? Where is our example? We have here the filter. This is the filter, sorry. Where it goes. Where is our signal Y? And the filter, I put here from the example num. It's our filter, it's num. Field. We don't need it. Let's do it. Where is, sorry, we have a Y, we have.
Maybe the one. You have three, like in line 40.
Ah,
40.
right. It's our, okay, now we will get it, I believe. Because filter is an object, we need two parameters. Okay, now we get it. Let me show it. Now, after using this field command, we will get exactly the same signal, but filter it without high frequencies. And we can see it by using zooming. Now you see the good filtering result of applying the filtering.
Why did we get the phase lag with the filter command?
Why we need this number?
No, why did we get the phase lag?
Because filter, physically, what is the filter? It's just the system, the dynamic system. When you put something in the input of the system and you will get output, there is a inertia between the input and output. Filter just a regular dynamic system. There is it has a frequency response function, it has a phase, it has an amplitude, and this is why there is a kind of delay between the input and output. Okay? Okay. If you don't need to use field, or you cannot use it, you can use another way of getting these zero characteristics. It's just to start our signal from the delay. Usually delay, this is the number, the half of the size of the filter. And using this delay number of the samples, you can just throw out the first delay number of the samples to your signal, and using, and to get the original number of samples, you just put at the end of your signal, you just need to put zeros. This is how it works. Let us show if, again, we will use our filter and we will apply, and we will use this we don't need. And this, you see the result is with the lag. And now let me here produce this command. Delay, we need delay. It's the length of the filter. What it was 100, it means that 50 we can hear instead of delay. We can use 50. This is the half of the length of our filter. Okay, this is a result of using another way of compensating this lag. Again, we have a very pure result. Also, I can show you the result of using filter to sound examples. Let me play the, and not play, first we should read to our workspace the sound of music that Matlab has inside. This is, let's read this example of sound, and then we will produce, and you should show some sound. Let me check if it works. You can see, you can listen, so you can hear the music plus noise, random noise. Can you hear? It was a noise inside the music, right?
Yes.
Okay.
Yes, we can hear.
Okay, now we will use the filter result. We can use the same Y as our music, but we need to produce the sound with the filtering result. Again, the same command sound, and now filtering. Let's see how it works. Okay, this way filtering works as a way to make a pure signal, so maybe just to throw out some errors or some influence from known source of errors, and very convenient way of using filtering. Again, I just insist that you feel the difference between windowing and filtering. Please remember that windowing is just playing with the signal in time domain, just pressing the end effects. And filtering is just using the frequency domain and increase or decreasing the part of frequency that we need. Any question about filtering and the windowing?
I have a question about the filter delay when I use it, so my function is straight without any frequency. Do you know why is it?
You know that here we can calculate when you use, for example, this function design filter, it produces not only the vector of the filter, it produces the object. This function produces the object, and we can calculate the delay by making group delay function of our filter. But you know, this is the same if you don't have, for example, your filter has only impulse characteristic and you don't have this design filter command, you just can use the length of your filter. For example, when I use the filter length 100, I already know that this delay is half of the length. Here the formula for this delay, half of the length of the filter. Delay is half of the length. Is it your question?
No, I said that my output from line 58 is the blue lines, and the orange one is straight line without any frequency, just 0. So I asked, why is that? Something went wrong.
Maybe you are speaking about this command field. Maybe you are speaking here from the command field. It produces filtering without delay. Because if there is no delay, it only could be done by two ways. The first way is just using this command field, and the second way is just change the number of sampling, just throughout the first part and add some zeros at the end.
I think she means that she gets she doesn't get the frequency. She gets frequency of no frequency, DC. This is what.
Yeah, exactly. Yeah, that's what I get, and I ask why, because I I think I did as you, but probably I'm not.
It means that you get DC value.
Yeah.
No, I only can recommend, just please send this part of this section, please send to me, and I will maybe analyze it individual way. I will maybe explain to you why it happened. It's difficult for me to understand because I cannot catch the reason.
Yeah, sure, I understand. Thank you. I will
send me, and we will discuss it later.
Okay,
Michael,
thank you.
Yeah.
Where first you define the variable num?
Yeah, we did it in our design filter example. Do you remember that we started design filter here? We started this design filter. Do you remember?
Yes.
A nice plot with it. And when we finished, I write the result of filter designing to our workspace. You can check my workspace, and you also, if you did it, when you ask what we have here, let me see. Where is now? I have not, but we can do it from the very beginning.
Yeah, this is why Matlab doesn't recognize this, right?
Yeah,
okay.
Right, because it should be, we did it already. We can do it again, but we have no time for this.
If we did it, it's okay. I will look at it after.
Yeah,
Thank you.
We did it maybe in video, we can see how we can save the result of producing filter, of making filter. The result of the filter itself, we just can export to the workspace by as a variable num.
Yes, I remember. Thank you.
Okay, you're welcome.
Variable itself, what is the meaning of it? Number of what?
The meaning of number?
What number of what?
I cannot hear. The number, what number?
What is this variable? What should we? What should it be? Like you exported it from the.
Yeah, this we can do it again. But this filter itself is just impulse characteristic. When we plot this and num, when we plot it as a graph, we'll see impulse characteristic. The filter physically, it's just impulse characteristics.
Okay.
For low pass filter, it looks like a decaying 1 degree of freedom vibration system. It started from 1 and goes to 0 with oscillation.
Ah, so it is a vector.
Yeah, it's just impulse characteristics.
Okay.
Yeah, you're welcome. Now, we have maybe not so many time for this. Let's do it much quickly. Also, I would like to tell some about preliminary signal procedures that we need to know before this Fourier analysis. Let's do it quickly. The decimation is just to throw out some points inside the digitizing. Sometimes we have too many points, and this decimation, it just decreases the sample rate of our data. And by integer factor, you can see, for example, from the beginning, we have again the sum of two sine wave, and the command of Matlab decimate. We get, we should do it twice. We should do it for time variables, also for the variables itself, for the y. And here we decrease the number of samples by 4. Let me show the result. The first subplot shows our original high number of samples. Here in the down plot, we have the same plot. You see, physically, we have the same. We don't need so large number. We get the same results, but just throughout and leaving only each fourth point in the sample. Okay, it's decimation. Very important for some kind of spectral analysis. Smoothing, I don't need to explain. You already know the smoothing. We discussed it in the previous meeting. Also very important, especially in our faculty when we play with the mechanical characteristics, integration. For example, if you have a sensor that can measure acceleration and you need to get velocity and you need to get the displacement of your signal, you should make integration of the acceleration to produce the velocity. How Matlab can do it? There is two functions. The first is cumulative trapeze or cum sum. Also, it could be this function, cumulative summation. I prefer trapezing because this trapeze, it's more, it computes the approximate cumulative integral using the trapezoidal method with the unit spacing. It's a little bit more precise than just pure summation, cumulative summation. Let's see the result. At the beginning, we built the sine wave for this time. And the second example is just integral of our sine. Let's see the result. Okay, let's maybe close everything. Okay. Now the blue color, it's our initial sine, and the red color is integral. You can see there's something unusual for sine. If, for example, sine is our function, as integral should be cosine, but this red function is not cosine, pure cosine, because it has a mean value, not zero. Do you know why? Anybody knows? Why integration, cumulative integration, produces this result?
You have a shift because you integrate it, so you have a constant shift over
Right, absolutely right. Because each integration, it has a constant of integration. Matlab doesn't know about this constant, but it depends of the initial value. When we start from sine or cosine, it's something arbitrary at the beginning, and this arbitrary just is staying there as a constant of integration. This is why if you play with the vibration analysis, after integration, you always need a low pass filtering or DC moving from this example, just to throw out this DC component that we don't need for our vibration analysis.
Michael, you have a new message.
Another examples of signal preliminary procedure is a differentiation. We need to produce a derivative of the signal. Also, there are some ways of do it. If we can do it directly by using gradient function in Matlab. Let me show the result. Again, let's plot our initial function. You see here is a small random noise just added to our example, and then we will produce the derivation using the gradient function. Let's see the result. Here, the result of differentiation. You can see even small noise in our initial signal will just make it not so good results of our derivative. This is why we recommend to use, for differentiation, to use not just directly this command diff or graduate. We just recommend to use different design filter as a differentiator. Here there is example of making this filter. Let's run this section. And running this section, we can use this filtering result now. Now you can see that our result is much more pure and clear and clean than the just directly using gradient or differentiation. Okay, and synchronous detection also the way of producing pure signal from the signal in noise. You can see the help of, or maybe in Google, just look for synchronous detection and you can see the results of this popular procedure and very, very useful procedure. Now, question about this preliminary result, please. Preliminary procedures, sorry, preliminary procedure, differentiation, integration, the trend, smoothing, and all that. Okay, no questions. Because I am just speaking fast because we need to tell something about Fourier. Okay, still, now we have time about Fourier, maybe 20 minutes. Basic spectral analysis, okay? In mathematical way, Fourier analysis is just, you can see, just summation of multiplication of our initial signal x by different sinusoidal or harmonic function, and making this multiplication and summation, we can estimate the spectra inside in our initial signal. This Fourier transform, it's performing dot product between the real signal and the various frequency of our sine. You can see here we just play with the k as a function from 0 to n, and k is just function, it's just frequency of our exponent, of our harmonic. For frequency analysis, for Fourier analysis, we need just terminology, where it's very important. We have initial sample data x, we need number of this initial data, we have a sample frequency of data, we have an increment in time, this is difference in time between two neighbors points, we have all the total time of our samples, we have the result of discrete Fourier transform, we have absolute value of this discrete transform, and we have energy or power of this initial signal. Also, we have frequency increment and frequency range. Some, if you have question, I will explain, but let's go to examples. Let's produce a signal as a harmonic of two frequencies. The first harmonic has an amplitude 1.3 and the frequency 15 Hertz. And the second one, it's a little bit more amplitude and higher frequency, 40 Hertz. Okay, let's plot our results. And also here we use the random addition to get something more complicated to see the power of the spectrum analysis. Here our initial signal x. Now let's produce the Fourier transform in Matlab. Matlab, it's very simple. To get today the Fourier transform, it's just 3 letters, FFT, fast Fourier transform, and we will get the result. Y is result of fast Fourier transform from our signal. Let's plot the result of this digital fast Fourier transform. I can tell you a lot of story of this digital transform, about history of this, but now we have no time. For this, I show you the size of our result, of our vector result. You can see that number of these samples in the results is the same as the number of our initial signal. In the input, we put initial 1000 point, and here again, we get 1000 point as a result. Also, we can see that the result of FFT is complex function. Each point is a complex. It has a real part and imaginary part. And we plot it here as an absolute value, as a model of this result. We can see that FFT from any kind of example, it could be complex function, it could be real function, but the result of FFT, it's symmetric result from the central line. It has symmetric part from the left and from the right. Why it happened? Because the FFT, this complex, it has a negative frequency result and positive frequency. For our practical meaning, we don't need this virtual negative frequency, we need only positive frequency. This is why for using the result of frequency of FFT, we need to have the half of the frequencies here. The frequency range is only half n divided by 2. And also the samples, also we need only half of them. Why here it's from 0? Because it's just the values itself, the frequency it's a value. And the index should start from the 1. This is why it's from the 1, and this here is +1. But again, we take here only half of our point because we need to play only for the half of our, only for positive frequency of FFT. Let's plot the half of our result here. This is line from 12 to 13. Again, why we have no, let me play the result. Okay. And also we can just, why we have no grid here? It should be gridding. Where is our gridding? Strange. Grid on, grid, it was my fault. Grid on should be here, not here. It should be only once. When we use grid twice, we just cancel the gridding. Here, the result of plotting only part of FFT. Again, do you remember that from the very beginning, we take the example, our first frequency was 15, and the second frequency was 40 Hertz. And in our result for the half of that, we have here, we have, let me show you. Here we have our 14 Hertz and our 40 Hertz, the second larger amplitude of harmonics. Also, we can find peaks. Matlab also has a very useful function to find peaks, to show the value of amplitude of each input, of each peak find in spectrum. For example, we can just plot it together, our spectrum together with this function of find peaks. This function find the peak, the amplitude value, and also the location, the frequency value. Now, please, do you have question about fast Fourier transform?
Yeah, about find peaks. I have a question. So you need to do you need to define a threshold for the, like, how does it know what peaks? Maybe the peak is very small and we don't need it.
Yeah, you are right. This is a very power function. It has not hundreds, maybe tens of parameters to help you to find exactly the peak that you need. Here, for example, I use only one of these parameters, mean peak height. That means that I don't need something here with the small peaks. I need for only these peaks. When I put here a small number, for example, this one, you can find a lot of different peaks. Let's check. You see how many peaks it finds when you don't need them. This is why here I use only one. I need peaks that are more than one. In addition to these settings, mean peak height, there are maybe tens other to help you. The distance between peaks you can ask, to the kind of any different kind. Please look to the help of find peaks. There are a lot of very pleasant things for us.
And what is the first vector that you put?
The input vector, our result of our FFT here is our FFT. Why? It's our result of calculation FFT.
Then why did you divide by n?
Again, because I need to find peaks, to find number of the frequency, and the frequency should be divided by n. Let us maybe here, you can see it here. You see, when the spectre, we have here, when we have a number of n of samples. To know the real value of frequency, we should divide by number and multiply by sampling frequency. This way we can find the real value of frequencies. We need to, because here, when we calculate the frequency, we need to know the number of samples. We need to insert it in this formula. Let's continue with FFT. What's the problem? The FFT is a very good, nice command. It can just estimate the spectrum, but there is one very, very serious problem with the FFT, because when we produce the FFT from the random samples, our FFT, our coefficients, Fourier coefficients, they also are random. When we produce several times of this FFT, each time it will be random. We cannot make some average estimation and decrease the result of our estimation of frequency, or maybe estimation of amplitude. This is why FFT, it's not so applicable in practice, because we need something that can be averaged and and can be used for random analysis to get result with a small number of standard deviation. This is why we use the square value of FFT, which we call power spectral density. To get the power spectral density, there is also different way for Matlab to produce this power spectral density. We can just make square of our absolute value of FFT here. Let's see this power spectral density result. Here we can see this our initial spectral for two harmonics, but the values, but dimension of power spectral density. It's squared FFT. Another way, it just using another common period diagram. We use our signal X, and we know the number of samples, and we know the sampling frequency, and period diagram just allow us to plot the power of this period diagram against the frequency. Let's do it. You see, it's absolutely the same. I use here, you see, I use hold on, I fix the previous squared function of the FFT to show you that this is the same. The number of energy is the same for FFT squared and period diagram. The third way of using power of calculation power spectral density is using the P-Welsh function in Matlab. It using a special window. Here we use a rectangular window, and we can calculate again. We calculate the power of our signal, and we calculate the frequency of our signal. Let's do it. Again, now three of them is the same. They have the same power and the same frequency result. Also, in addition to power spectral density, we can produce power spectrum. Another command in Matlab, power spectrum. And this produce power as a function of frequency. Let's do it. Again, we have here the result of power spectrum. And all this function, FFT, power spectral, everything, it works not only with the real function, they also work with the complex function. Here, the examples for complex function you can have here, we will not discuss and consider now. we'll go directly to the spectrogram using the command, very power command spectrogram. Let me explain how it works. Here we have a chirp example. We all should already know what is chirp. It just have different and varying frequency in time. And this chirp with constant amplitude but varying frequency can be analyzed using this spectrogram. What is good for this spectrogram, it can also plot, not only calculate the spectrum, but also plot it. How it use this spectrogram? It use FFT many times using short segment of signal. Our signal has several thousand points inside. Each point we ask to use 128 point each segment, and each time it uses FFT, and then the program spectrogram, it plot the results together. Let's see how it looks. You can see this result of spectrogram. Spectrogram is just a graph in time and in frequency, and color show the power of our signal. The more yellow color, the more amplitude of the signal. We have signal that is changing in time and in frequency. This is spectrogram. The same spectrogram can be plotted as a 3D. To plot the same spectrogram, we should use result the same spectrogram, but with the left hand side of the spectrogram, and using the surface to plot the same as a 3D plot. Let's do it. We just uncomment our result, and we run this section. Here, speaking the truth, it's absolutely the same as before, because when I show you this way, the spectrogram, it's just the same. You can see the time, the frequency, and the color. But here, the amplitude, it's not only the color, it's also the height of our graph. It's also more beautiful and maybe more clear in many cases when the signal is complicated to see as a surface. It's much more maybe convenient to understand the result of spectrum analyzing. Any question about spectrogram, please? Okay, we also, this spectrogram we can get not only by using command spectrogram. Matlab also have powers PS spectrogram, also the same result. Let me show you. We can plot it in just a graph in 2D domain, and we also can plot it in 3-domain plot. Just uncommenting this, and we will get here the result. The command power spectral is it uses the filtering and smoothing. This is why this result is more clear, maybe more beautiful. Okay, it's not again. Let me show you the Matlab also for those who is not convenient the different kinds of window and signals. We can use signal analyzer to analyze the signal. Or maybe we will not, because it's only 7:20. You yourself can just play with the signal analyzer and understand. If not, maybe we'll get time at our last meeting at Thursday, and we will discuss it. Let me show you the frequency response function, but we have no time for frequency response function. Please, what is the meaning of frequency response function? When we have some input and we get output from the system, using the input and output as a pair of signal, we can estimate our frequency, our system. We can get as a graph frequency response. We have a get a system as a transfer function. And it's very useful for analysis of in experiment and in a theoretical way. Also, it's very useful tool for control technique when we need to know about our system, when we get something input and output to understand the system, what is inside. We have no much time. Let me maybe show the last example that I prepared to how to use this frequency response analysis in real example of real object. Please, I send to you this file and it should work here. Let me start the last line in this R35, the last line. When we start it, we will get model of the real flexible aircraft, and this file show how to make this analysis of frequency response function when we use experiment. We have one shaker to excite the system, and each wing have 20 accelerometers to measure the output from this result. We can run this example, and this example will show the procedures of estimation frequency response, but we have no time to see this frequency response. We can stop it and close. Just let me show you the result. Here the time frequency domain and frequency itself, the frequency response function, and very important result of estimation, the model parameters, because this just graph as our amplitude depends on the frequency. But for example, mechanical engineering, it's very important to know what is the resonance frequency, exactly the resonance, what is the mode shape, and what is the decrement or damping of this system. Everything can be done using the frequency response function analysis. And as a result, in the mechanical part of analysis, you can see here the active GIF result of model analysis, which show us how the wing moves at each vibration frequency. Here, for example, you can see the frequency, the 7 Hz frequency, 15 Hz frequency, and how the wing changes. Also for designer, it's very important information, because we can understand if the displacement of our movement is too large, it can be destroyed, this wing. And constructor or designer should know where our location of this critical place in our construction. Okay, now we finished. We have already 2 hours we used for our. Now, please, questions for this first, for this last kind of examples of model analysis, and also for identification. I am ready for questions, please. Also, at the end, maybe now, after our meeting, I will send to everybody this question that was built by Edeline, and please answer, please send your answer to this work, to this Google Doc, and this way we can understand which way of our meeting it's it's better for you, or sending just pure and script without lines, and we will work together. Or this way, as we tried today, you will get everything already ready. You just need to run each section and understand how it works. Please, question for all the subject for today, and maybe not only for today.
What is the subject of the last lesson on
the last, for Thursday evening, we will speak about wavelets. We will speak about Hilbert transform, and non-linear, non-stationary signal decomposition. Because here, what was today, it was just sine, cosine, just simple signals. But in reality, we have more complicated signals, which are not stationary. They are sum of varying signal in times. And we need to know how to decompose, how to extract from this composition, how to extract the result of our signal analysis. And who is interested in wavelets and Hilbert, you are welcome to our last session Thursday evening.